Okay, here's some examples out of your notes on how to do these different problems with acids and bases. Like I said, I'll also do a couple examples off of your assignment, just so you can see how to do it, like when you actually get to doing your assignment. Okay, so for the first one here, classify each reactant to the following equations as a Bronsted-Lowry acid or a base. Okay, so again, acid means proton donor, so it has to have a proton in it in order for it to be an acid. So this is going to be our acid, meaning this will be our base. Okay, and just to kind of help you out, we'll do some conjugate acids and bases. Like we'll look at the pairs as we go through here too. So again, conjugate acid-base pairs, you take away, like you take this hydrogen, it's going to go over here. So the conjugate base of the acid would be this conjugate base, and then this would be a conjugate acid. And so again, we should always have an acid-base pair on both sides. Okay, for here, we have no hydrogen, so this has to be our base. Okay, here and like remember for organic acids, which we'll talk about organic acids more in the next organic unit. Okay, but for organic acids, this is the H that makes them acidic. These H's don't count. Okay, and so when we're looking for like polyprotic, things like that, you're always looking at how many H's come off the COO. Like is there C, like if you see a COOH2, then it'd be polyprotic, things like that. Okay, but anyway, this is our acid. This would be our conjugate base because it's our acid without its proton, and then gave the proton over here, so this is our conjugate acid. Okay, next, this again, we look for the protons. This is our acid. This then is our base. This would be our conjugate base, even though it still has protons, but because it gave one of those protons away, it's our conjugate base. And then our base gained a proton, so it's our conjugate acid. Okay, next one here. This one, they both have protons, so they can both be acids. They both have charges, so they can both be bases. So we have to look over here which one gave it up. So because HSO4 minus becomes SO4 2 we know that this H had to be donated over here. And so since this gave away its H, it's proton donor, that means it is our acid, meaning this is our base. And then over here, SO4 2 because this is our acid, it becomes our conjugate base, and this is our conjugate acid. And so the rest of this page is just more notes. Okay, you can look over, and I've probably talked about them in the other video. Okay, here are some more examples from page 8 of our notes. Okay, so evidence indicates that hydrogen sulfite ion is amphiprotic. So hydrogen sulfite is HSO3 2 Okay, a sodium hydrogen sulfite solution can partly neutralize either a sodium hydroxide spill or a hydrochloric acid spill. Write the net ionic equation for the reaction of aqueous hydrogen sulfite ions with hydroxide ions solution. Label a reactor as acids and bases. Okay, so we have hydroxide, okay, and it is mixing with our hydrogen sulfite, or it should just be minus, sorry. Okay, they're both aqueous, we mix them together. Should have our double arrows because everything in here is at equilibrium now. Okay, so this has to be our acid and donate its proton here because this is our stronger base. Okay, and so we get SO3 minus, or 2 minus. Okay, and so if this is our acid, this is our base. Okay, this would be our conjugate base. Okay, and then it's going to form water. Okay, and so this would be our conjugate acid. Okay, so that would be our reaction that's taking place again. Like if it says we have sodium hydrogen the sodium doesn't matter because it's a spectator ion. Like it'd be NO3 or Na plus on this side, Na plus on this side. So instead of writing it out twice, we just know it's a spectator ion. We don't worry about it. Okay, and then for this one, if the hydrogen sulfite reacts with hydronium, so let's write that out. SO3 minus plus hydronium, H3O plus. Okay, again, if like you are ever wondering which one works as an acid or a base too, you can always check your table. It'll always be the stronger acid will be the one that gives away its proton. Okay, so even though these can both be acids, this one's stronger. It's going to give one of its protons over here. So it's going to form H2SO4, or SO3, sorry. And it loses a charge because it gains that H plus. And then once we take something away from, or a hydrogen away from that, it becomes H2O. Okay, and so this is our acid. This is our base. This is our conjugate acid and conjugate base. All right, and Bronsted-Lowry definitions identify the two conjugate acid-base pairs for each of the following reactions. Again, so again, I look here, this is my acid, this is my base. So the conjugate acid-base pair, you just should differ by one hydrogen. So this would be my other conjugate acid-base pair. So this is the base, conjugate acid, acid, conjugate base. Okay, here, this is my acid, this would be its conjugate base. So that's, okay, this is my base, this is its conjugate acid. And they should always differ by one hydrogen. For this one, this is my, it's given away, so this is my acid, this is its conjugate base, this would be the base conjugate acid. Okay, here we have water, water is amphiprotic. Okay, so it doesn't really matter which one you have as the acid base, one's going to give away its proton, one's going to gain it. Okay, and so, like in this case, if this gives it away, this is my acid. Okay, this would be its conjugate base, this would be the base, and the conjugate acid. All right, these examples are on page 11, so it's just using the 5-step method to predict the predominant reaction in the following chemical systems. Okay, and so this is where 5 steps label what you have in your system. So we have hydrofluoric acid, HF aqueous. Okay, and aqueous solution of sodium sulfate. So again, we break up, or sorry, sodium is just 1 plus, and then sulfate, SO4 2 minus. They're mixed together. Okay, and so now we label them as acids and bases. So HF, okay, is an acid. Okay, Na, this is Na plus. I'll erase. Let's make that a little bit neater here. Oh, didn't erase. Okay, Na plus. That's a spectator ion. I know that, so I'll just kind of cross it out. And then SO4 2 minus is our base. So we're going to have HF plus SO4 2 minus. Okay, the H is going to be donated over here, so we're going to get F minus plus HSO4 2 minus. Okay, so yeah, step 1, label your entities. Step 2, label them as acids and bases. Step 3, write out your reaction. And well, I guess step 2 is label your acids. Step 3 is your bases. Step 4 is put up your reaction out there. And then step 5 is to predict which direction it'll favor products or reactants. So for that, we look on our chart here. So I find my acid is here, my base, okay, SO4 is actually up here. And so this is going to favor the reactants because my base is above my acid. So I'm going to say just on their reactants. There you can just give an arrow showing which direction it favors. It's up to you how you want to do that. Okay, this next one, so strong acids such as perchloric acid. So we have perchloric acid. Remember, any acid above hydronium, so all of these acids here, so perchloric's right at the top here, we just write down hydronium. Okay, we don't have to worry about anything else. As soon as we see that strong acid, we write down hydronium. Okay, and then same thing here, like we know, again, sodium is a spectator ion, so we'll write it down, but really we aren't going to use it. And then we have hydroxide. Okay, so this is our acid, this is our base. When we put them together, H3O plus OH minus, they're going to produce two waters. Okay. Methanoic acid is added to an aqueous solution of sodium hydrogen sulfide. Okay, so I wrote our entities here. Now I'll label them as acids and bases. Okay, remember some can work as like an acid or a base. Okay, and so you will have to label some as both. Again, sodium spectator. So this is our acid. In this case, this is our base. And you can just check again your chart. Okay, HS is here. Okay, HS I can't find on the other side, so I'm not going to label it like it might be a weak acid, but it's not even on our chart, so we aren't going to worry about it. So now I just put them together for a reaction. Okay, so there's my balanced reaction. Okay, now I just check my chart. Okay, so formic acid is here. Okay, I gotta keep scanning down. Here's my HS minus. So my acid's above the base, so it's going to favor the products, which I forgot to do in the last one, but hydronium's basically at the top, hydroxide's on the bottom, so it's going to also favor products. Okay, student mixes a solution of ammonium chloride. Okay, so we have ammonium, NH4 plus, and chloride, Cl minus. Okay, and sodium nitrate, Na plus, okay, and nitrate, NO3 minus. Okay, we look on our chart to label them as acids and bases. Okay, NH4 is an acid, Cl minus is a base, but actually it's above water as a base, so we're going to not even worry about that. Sodium is spectator ion, and then NO3 minus, it is a base. It's also above, so actually I'm going to label that as a base also. Oh, and one thing I've been forgetting through all of these, they're all in aqueous solutions. They should all have water as part of them. Okay, and so that, in this case, water is our strongest base. Okay, because these ones are above water, so it's not even part of it. So our overall reaction is our strongest acid, ammonium, plus water, and it's going to produce ammonia plus, so it's H3O plus. Okay, we look on our chart. Again, water is above hydronium, and so this is going to favor the reactants. Okay, another way when you're doing these, and like if you don't have the chart, well, you'll always kind of need that chart handy, but like whichever side has the stronger acid, that's the side, like it'll always push the other way. So since this is the strongest acid, it's going to go that way. Okay, since if we look here, this is our strongest acid out of all the different things I have here. Okay, it's going to favor the products. Okay, and so I just look at wherever my strongest acid is, it's going to favor the opposite direction. Okay, and so this one, nitric acid. Okay, nitric acid is a strong acid, so it's going to be H3O plus. Reacts quantitatively with sodium acetate solution. Okay, so we have sodium, we have acetate, CH3COO minus. Okay, and then we have water, okay, which I've been forgetting. Okay, this is our acid. That's spectator ion. This is a base. This can be an acid or a base. Okay, this is my strongest base. This is my strongest acid. So we have hydronium plus acetate, and it's going to form, oh, the double arrow. So this will give one of its protons over here, so it's going to form acidic acid and water. And again, whenever we have a strong acid, okay, it's going to favor the products always. Like if we have a strong acid in our reactants. Okay, for this next practice, for the following questions, select one of the following. So of these three, which is the strongest acid? So I just look on my chart, okay, whichever one under the acid column is closest to the top. Okay, which like it's going to be this HSO4 because it's only 3 down from the hydronium ion. Okay. And you'll kind of get used to going through this chart and knowing where different things are. One thing to note, be careful of like HNO2 is a lot different than HNO3. So HNO2 is nitrous acid, HNO3 is nitric acid, which is a strong acid. Okay, which acid has its strongest conjugate base? So again, the strongest base, conjugate base, is closest to the bottom. So I just look at which acid is closest to the bottom in this case. And so it's going to be HCO3 because its conjugate base is actually only 3 up from hydroxide, which is the strongest base we can get. Okay, and that does the direction of the following reaction favor the reactants on the left or products on the right. So again, look on here, okay, and just see, like if this is our acid, this is our base, this is our conjugate acid, this is our conjugate base. What acid, or like if our acid is above our base, which if we look on the chart, it's not, so it's going to favor the reactants. Okay, or another way, since this is our strongest acid, it's always going to go away from that.